Hi guys, I will be talking about circular motion in this video. Alright, circular motion, we basically have two types of motion, one in a straight line, the other is in a curve. So the one in a straight line is called linear motion and the one in a curve is called circular motion. And we have a lot of different examples of circular motion. Alright, so force on a circular motion. So the force that is keeping the object in their circular orbits. Alright, the force that is keeping the objects in their circular orbits, they basically have a special name, and that name is centripetal. And centripetal means center seeking. Alright, we're going to be digging into that definition a lot more in detail, but we need to know this first. In a circular path, we are going to have a force that is keeping objects in their circular orbit. Alright, if you didn't have that force, they wouldn't be able to have that circular motion. So that force that is keeping the objects in their circular orbit is called centripetal force. Alright, so what is going to be the equation for that centripetal force? When you actually do some investigation, then you will see that the mass and force, they are directly proportional. As mass increases, force increases. And velocity and force are also going in the same direction. So as velocity increases, you will have more force. But you will see that when velocity increases a little bit, force increases more. Then they actually have seen that there is a different relationship. It's not just direct relationship. And as the radius increases, the force is getting less and less. So when you put all of those forces or all of those criteria together, then you basically get the idea of the equation of centripetal force, which is mv squared over radius. Alright, so this is centripetal force. What is centripetal force? The force that is keeping objects in their circular orbit. And of course, if there is a force, there must be an acceleration, because Newton's second law says F equals mass times acceleration, which means if there is a net force in a system, then we expect this system to be accelerated. So then in this case, we look at the equation. It is a little bit similar. F equals ma, but for centripetal force, we have mass, but a is not just a, it is basically v squared over radius. Then we basically say centripetal acceleration is going to be v squared divided by radius. And direction of centripetal acceleration and force, if you go with the direction, so for uniform circular motion, speed is the same, but there is still acceleration. So we're talking about a constant velocity. However, we are talking about acceleration. So how do we get acceleration if velocity is constant? So remember, acceleration is change in velocity over time. But what do we say? It's change in velocity. And remember, velocity is a vector. So that means if direction is changing, then you can still have acceleration. And that's what's happening. If you look at the velocity vectors, they are not going in the same direction. So once you do the delta v, which is v final minus v initial, you are seeing that you have extra vector right there. And that is basically your centripetal acceleration, and that's how you basically form it. And acceleration is due to the change of direction, and the direction of the acceleration is going to be towards the center. All right, and acceleration and force are going to be in the same direction. So centripetal force and centripetal acceleration, they're going to be basically going towards the axis of rotation. All right, so that is very important. All right, calculation of centripetal force. So when we are calculating centripetal force, we need to figure out that centripetal force is not a new type of force. All right, so centripetal force is the force that is keeping the objects in their circular orbit. So in this case, for example, if the mass is able to stay in that circular orbit, there is one force responsible from that, which is tension. So in this case, tension is my centripetal force. So that means tension is actually equal to mv squared over radius. All right, so in a free body diagram, you do not show Fc because Fc is not a form of force. It is a name for the force that is keeping the objects in their central circular orbits. All right, so considering that, I'm not going to be talking about all of the details of that. I will just show you and tell you they exist over here, so you guys need to look at the details of those. So one of them, the first one is horizontal circular motion. So in this case, tension is the reason that this guy is able to stay in the circular orbit, so your centripetal force is tension. In this case, the reason that the car is able to stay in the circular orbit is friction force. That's why friction is going to be the centripetal force, and then you do the math after that. But if you're talking about vertical circular motion, then cases is going to be a little bit different. So tension is the reason that it is able to stay in the circular orbit, but depending on the location of the object, it is going to have actually different force diagrams, because in the first location, tension is the only force that is going towards the center, but once it's on the top, gravity and tension are going towards center. Then your centripetal force is going to be tension plus gravity. And at location 3, Fg is not going towards center, so only centripetal force is tension. And at point 4, Ft and Fg, they're going against each other. So the net force that is going towards the center is basically Ft minus Fg. So as you can see, if we are talking about a vertical circular system, then we are basically going to have different centripetal force depending on the location of the object. And the second case is very similar, but instead of tension, we are going to have normal force in the system. So normal force is basically replaced with the tension, but the rest is the same. All right, so we can also have angled horizontal circular motion. So in that case, again, we are looking at our circular motion. So circular motion is happening in this region. What does that mean? Your center axis of rotation is this location. So we are looking at the force that is going towards in that direction as centripetal force. So regular free body diagram is basically Ft diagonal up and Fg going down. So there's no force that is actually going towards left. But what do we need to do to be able to figure this out? We basically need to find the x and y components. So we basically find tx and ty by using cosine and sine. Then we are able to see that this tension is going to have x component, which is going towards the left, which is this axis of rotation. Then my center of my centripetal force will be tx. So then tx will become mv squared over radius. But most of the time, this is not going to be enough for those type of questions. Then you also need to be able to make a connection in between ty and fg. Since there's no acceleration in the up and down direction, then we also know this fg and ty, they're equal. So when you put those two together and this guy together, then you're going to have this final equation. All right, if you have a banked curve, then what's happening if there's no friction? Again, the axis of rotation is going to be going in this direction. So Fn, Fg, they don't have a component in that direction. So in this case, once you look at the forces, you will figure out that Nx, x component of the normal force, is going to be going towards left, which is axis of rotation. So your Nx is going to be the centripetal force. One thing that you guys need to be careful about this scenario is your x and y is regular x and y coordinates. So normally when we were talking about incline, we were basically tilting the x and y, but to be able to actually solve for the centripetal force, you do not do that. You just keep the x and y coordinates as it is, and your Fg is still just going in the y direction. Your Fn is going to be the force with an angle, so you need to find the components of your normal force. And if you have friction additionally, again, keeping this guy as x and y, then you're going to have two basically forces going towards the center. So the x component of the normal force plus x component of the friction force. So basically nx plus fx is going to be your friction centripetal force, and that's a lot more messier than just finding the normal force components and friction force components. You should also consider that nx plus fx is equal to mv squared over radius. That's what's happening on the x-axis because there's a circular motion on the x-axis, but on the vertical we just have forces going up equals forces going down. So ny equals fy plus fg. When you put all of them together at the end, you basically get that messy equation. Again, they're there for you to use as a reference if you guys need it. I'm not sure if you're going to need them. Alright, circular motion is basically going to continue with gravitational force. What is the reason for gravity? It's always surprising to me, but the mass is the reason for that gravitational force. So, true nature of gravity is basically the mass that we have. And what is gravitational force? It's basically gravitational force constant times mass 1, mass 2 divided by distance squared in between those two masses from their centers. And that gravitational force constant is a really small number. So that's why we are only going to be able to talk about gravitational force if either of the masses or both of the masses are huge, so that we can actually observe a significant gravitational force. But in nature, every mass, that's what that equation says, every mass has force. All right, so they all pull things to themselves, but they're significant if this mass is a number that is in the scale of 10 to the power of 12. Alright, what are the properties of gravitational force? Gravitational force acts on both of the masses that are interacting. So if we have a mass 1 and a mass 2, you have force on both of them, and they are equal in size. So we're talking about Newton's third law over here. And distance is measured from their centers, so not from their surfaces, from their centers. And gravitational force has no push force. It can only pull towards itself. That's why they are talking about anti-mass, because all of the charges, they have positive and negative. So they have plus attraction and repulsive forces. Magnets have north and south pole, so they also have attraction and repulsive force. And they are basically only seen observing mass being pulled. So that doesn't really make sense for them, or they are expecting more, which is anti-mass, and then mass can also have a repulsive force, not just an attractive force. Anyways, that's an extra information. Alright, so how do you calculate the gravitational acceleration? So we say when we drop things towards Earth, they basically accelerate with g. So then we basically say the force on an object on Earth is basically mass times gravity. But true nature of gravity doesn't say so. True nature of gravity's force says two masses are going to apply force to one another. So if we are basically talking about the system Earth and any object, so our two systems or two masses are Earth and object. So when you drop the object, it basically goes towards the Earth. So that means the force in between two mass is object's mass and the Earth's mass. And the distance that we're talking about is basically from the center of the Earth to the basically object. So in this case, this distance is basically going to be radius of the Earth, roughly. So then when you consider FA, F equals ma, and true nature of gravitational force, then the force that we're talking about over here is Fg. And once you put the true nature of the force, then you need to go with m Earth, m object divided by radius of the Earth square times g. And the thing that is accelerating is object, so mass object times a, and A is going to be this. And once you actually put in all of the numbers into the equation, then you will see that A is the number that we know of, which is 9.81. So basically, gravitational acceleration on our Earth is depending on those properties: gravitational constant, mass of the Earth, radius of the Earth square. So as you can see, it doesn't really depend on anything. It only depends on the properties of Earth. So just like this, you can actually set this equation for any planet. So gravitational acceleration of any planet is gravitational force constant times mass of that planet that you're on, and the square of the radius of that planet. So that's how we basically find the gravity on any planet. All right, satellite motion. Satellites are also having a circular motion, and the force that is keeping them in their circular orbit in this case is that true nature of the force again, two masses. So we have Earth and the satellite. But they are basically having a circular motion. Then what are we going to have? We're going to basically combine that gravitational force and the circular motion. And the force that we have is basically G, m satellite, m Earth, divided by radius. So we don't consider radius of the Earth because radius of the Earth is this distance. But you have a little bit more distance, and you cannot just ignore that distance because it is a significant amount. So we don't just say the radius of the Earth, but it is the radius, which is going from the satellite to the center of the Earth. Or you can just put that as radius of the Earth plus altitude, which is this region. All right, so, and when you think about it, satellite is making a circular motion, so it's going to have a centripetal acceleration, which is mv squared over r. And when you combine them, you will see that the mass of the satellites will cancel out. One of the r's will cancel out, so v squared will become mg over r. Then v itself will become square root of g, mass of the Earth, divided by radius. And as you can see, the velocity of the satellites around any planet, again, depends on one thing: the radius that they need to be at, and the mass of the Earth that they're around, or mass of the planet that they are around. All right, what is gravitational potential energy? So far we talked about gravitational potential energy as mgh. And one thing that we were talking about gravitational force, we were talking about a reference point. So, for example, if you have systems, we were able to choose 0 point as whatever we want. So if you are above that point, you were basically having a positive potential energy. If you're below this point, then you were basically having a negative amount of energy. So that positive and negative basically was depending on that reference point. But true nature of the gravitational potential energy arises from the law of gravity and is equal to the work done against gravity to bring the mass to a given point in space. And because of the inverse square nature, so once we think about gravity being equal to gm1 m2 over distance square, as this distance goes higher and higher, this force is getting less and less. So that means at infinity, we basically have no force required to actually do the work. So that means our true zero reference is not any point that we want. True zero reference is basically, considering that this is the Earth, true nature or true 0 point is basically the infinity. So what does that mean? Anything below that is going to have a negative sign. All right, so the sign of a potential energy is basically negative. And once you basically represent, well, that's not how we actually get this final equation, but I just basically fooled you over here a little bit. So all you have to do is basically replacing the g in that equation in the height. So since we are talking about motions on the Earth's surface, then the distance that we are talking about is, again, almost equal to the radius of the Earth. So your height is basically the radius of the Earth. And g that we were talking about, we were just using it as g as 9.8, but true nature of g is basically g times mass of the Earth divided by radius of the Earth square. And once you put them into the equation, then what do you get? One of the Earths are canceling out, and we define this negative sign because true zero reference is the infinity. Anything below is going to have negative sign, so your potential energy is actually going to be as follows: negative g m object m of the Earth divided by radius. It's pretty close to the force. Force has extra square over here, but the potential energy doesn't have it. All right, what's escape velocity then? So escape velocity is defined as the minimum speed an object needs to leave from Earth's gravitational field. So if you think about, you basically throw things, they are basically coming close back the Earth. But if you have a certain velocity that it is going to be able to actually leave the Earth, and once it leaves the Earth, it is going to have basically no velocity at all. All right, and that's basically the minimum escape velocity. So it's basically the critical point. You are not going to go back down to Earth, and you are not going to be continuing to move after you leave the space, leave the gravitational field of Earth. So, and the other thing, once you leave, you are basically out of the gravitational pull of Earth, so you don't really have a gravitational force either. Then a way for us to construct the equation is basic conservation of energy. Initial energy is equal to final kinetic energy. And at the end, we expect no potential energy and no kinetic energy because we are talking about the minimum velocity. So once it leaves the system, like the atmosphere, it's going to basically stop, because as it's going up, it's basically slowing down, slowing down, slowing down. You're going to reach that critical point that you're off the gravitational fields and you are done. You don't have any more speed. So that means you expect your final kinetic energy being 0, and you expect it to be leave the potential gravitational fields. So you don't have any potential energy at that location. So then what are we going to have? We are only going to have initial kinetic energy, which is 1/2 mv squared. But the v that we are defining over here is going to be the escape velocity plus the potential energy that we are talking about. And how do we calculate the gravitation potential energy? Negative g m object m Earth divided by r Earth. And once you put them together, you will see that the right side is 0 and the left side you have positive and negative. So then the final equation will become your initial kinetic energy is equal to positive gravitational potential energy. And when you basically cancel those out, your escape velocity will become that nice equation. That's how we find the escape velocity of objects. All right, that is it for circular motion. Thank you for watching. See you in the next video.